Actualmente es profesor investigador de Citedi y sus áreas de interés son el análisis y control de sistemas no lineales y sus aplicaciones, particularmente control H infinito no lineal, control de estructura variable y sistemas subactuados. Ha publicado 24 artículos en revista de alto índice de impacto y 130 artículos en congresos nacionales e internacionales. Ha graduado 6 estudiantes de doctorado y 10 estudiantes de maestría y actualmente es miembro del Sistema Nacional de Investigadores SNI nivel 2. Los dejo con el doctor Luis Tubac.
My level of biggest control of undirected mechanical system. So, but in particular, I'm going to take account the motion control of this kind of systems using two-rate approach. And the second one is the non-motion control of mechanical system with actuator jet form. Everyone's motion control under actuated mechanical systems using the two-relay approach. It's a work with Professor Friedman. So, what is under actuated mechanical system? The mechanical system is having less, our mechanical system having less actuators than the number of degrees of frequency. There are several examples of this kind of systems, like the academic, the Vanderbilt, Acrobot, initial pendulum, and so on. But also, we can find applications that involve robots, aircrafts, and also including fully actuated mechanical systems, but with under actuated failure. It becomes this kind of systems. So, what is the idea? The problem is to control, to produce a motion control in under actuated mechanical systems. So the idea is how to produce an output of this mechanical system, that's oscillatory output, using a discontinuous feedback action without reference signal. So we use here something that we call two-relay control. It has this kind of structure. C1 and C2 are constants, and it can be positive and indeed it can be negative or zero. Depends on the frequency or the amplitude. So, two main questions we start on. Is it possible to have a product motion in this kind of systems? And so the answer is yes. And we can have the solution in the application from Leonard Friedman and Ingo Wolf. The second question is it possible to find values of C1 and C2 such as selected output by converts to a limit cycle with desired frequency in amplitude? So this is the main research that we have done with this group. We take into account, so we start with these structures. So, indeed, we did three methods to find frequency and amplitude on the output to generate periodic motion in this kind of systems. But we start with this one, describing function method, which provides an approximate solution of the periodic motion in this kind of relay feedback systems using this kind of the relay controller. It depends on the error and the time data of the error. What is the describing function? Describing function is what's used for linear systems and it's based in the Nyquist plot the plant. So the intersection of the describing function is a straight line with a slope which depends on the relation between ratio C2 and C1, which can be located in any quadrant. This is a mistake here. It can be located in any quadrant of the next plot. So the intersection between the function, and the matrix plot provides exactly the solution of the Prandtl motion. We have here then the frequency and amplitude of this motion. How to compute these parameters C1 and C2? So, the first condition, we set amplitude and frequency of the motion. Now we need to compute those values. So we compute here's the imaginary parts of the function and the real part. It depends on the frequency, which is known. Then the amplitude is given by this equation, the equation, where C1 and C2 are known and amplitude is fixed by the user. So by simple algorithm, using this value, C1 and C2 depends on the amplitude and the radio C1 and C2, the frequency. And so C1 can be computed depending on the sign, depending on the place where the matrix plot is located. But we step forward to experimental results. So we have 20 minutes, so we have many details. So we go to the experimental result. Sorry, to the experimental application. In this, we take the initial wave pendulum. This is a model of the initial wave pendulum. So we need to lose the side frequency and the up and the around this zero point. So we need to compute C1 and C2. Now, because we're dealing with describing function methods is made for linear systems, but indeed we have a nonlinear system. We need to compute the final procedure to linearize the systems. We can use Taylor, but indeed in that we use this normal form method. We consist of a change of variables with the place of Q, Q1, and Q2. Then finding the time derivative of this function, you obtain this linearization of the model. So the input control is going to generate oscillation at the output of the initial pendulum is given by this equation. So this is obtained by obtaining a third derivative of this eta function. So these terms compensates nonlinear terms, and this term in red is used to generate the oscillations at output of the systems. It's not important not to confuse with the twisting controller, because the twisting controller have several conditions like C1 invariant C2, and this one output must be true, it will be positive. So we show this quiz. We have here this computer. There is a system and motor over here, and this is only encoded in the joint and encoded in the velocity of the encoder in the motor. So using that argument that we proposed in the last slide, we generate this element of the root motion. We change the value of C1 and C2 to decrease the frequency online. So we increase the amplitude and increase the frequency. So what is the main advantage of this methodology? More or less the advantage of the structure. We don't have robustness. So now the system is acting like an open loop against, let's say, the disturbances. How to deal with this kind of problem? So we change. So this is the experimental result. So we have two problems: friction and on the kind of disturbances, external disturbances. So now with Professor Friedman and Gabriel, we make some work about to deal with robust robotics. So we change the structure of the overall systems. This reference model now is a like structure of the inertial ball pendulum using the two relay controller. And this controller can be anyone. We use a twisting controller in order to add robustness to the overall systems. The reference model is now has a new structure. The main difference between it was not necessary to include musical friction here to produce to generate oscillation and the output as a reference signal. So, how to synthesize the controller is not very easy. So, we will signal like an error position, the position error. We derive we have the time derivative twice. We have this dynamic, including the disturbances that can work in the velocity and the position. The controller, the wheel thing, has this, we eliminate nonlinear terms, we have some proportional derivative terms, and here is the twisting algorithm, where alpha 1 plus is larger than alpha 2, larger than this bound of the disturbances. So the closest system that we didn't obtain was summarized here. Here we have the sigma is given by this equation, and the velocity have this expression. So now we need to find to prove that this system is asymptotically stable, open stable. So summarizing, the Lagrange function that we propose include the position. Error position goes to 0, asymptotic goes to 0 was this one, and the time derivative was this is one strict Lagrange function, and the time derivative of the whole thing was here. It's important here that alpha 2 is larger than bound for the disturbances, and yes, larger than the bound of the disturbances. And B2 and beta 2 larger than the. So now we are going to present some new movies with these experimental results. I have the experimental results here. It is now the position error and the position error under some disturbances. Okay, you can see that the disturbances are close to 0 despite of the existence of disturbances and viscous friction. So what is the challenge now with this kind of problem? The extension of the results to power converters to deal with degree of underactivation greater than 1, yet also with the position filter case being analysis, and for example with another various structural control algorithms to generate precision motion at the output of the systems. So that's summary contribution of this topic goes from the filter from the system of control. So we make here a very simple example here we make a sky function method with a very simple, with a blue pendulum example and application. In this paper from the International Journal Control, we make three theoretical contributions using the scaling function method with an approximate solution. The LPRs make an exact solution for the amplitude and the constancy 1 and C2. And indeed, we make contribution in the nonlinear system with Hungary maps. But this is still more difficult than algorithm to train the solution. Then, finally, for preparing the International Journal of Works and Nonlinear Control, make proposed condition of sufficient and necessary condition for extensive excess of the theoretical solution. And finally, we make this contribution of the Rose solution of the practical control of the initial group area. Also, it's important to mention that all the people who collaborate together, starting with Professor Len Friedman, of course, Professor Igor Boyko, and Leonid Fedorich from the University of Miami, Rafael Lidiardi from NAM, Dr. Antonio Estrada, and all students, graduate students, clinical class. When we explain out the second problem, the non-smooth HBT control mechanical system with actuator jet zone. It's more or less the same problem that we start to work on.
Summarize the previous part of whether such control allows you to overcome some limitations of
Yes. Let's start with the means that we start. Professor Leonid Friedman and Professor Boyko use this method, scaling function method, to analyze such shattering of the twisted level. So we make the opposite. Okay, let's say we take the same controller, we change the values to which is the C1 and C2 to be positive, to be negative. Okay, and we have this hypothesis to think, okay, we can have less frequency, more amplitude, and to get, okay, let's aggregate the most complicated problems and directed mechanical systems. And I said, we make the test in the lab of Nonlinear and it works. And it works.
So you have dragged out the Hungary.
Yes.
You have dragged right?
Yes.
Before,
yes. It's like equivalent to put our poles and zeros in the imaginary X. It's same equivalent.
And can you relate it to Roger Roberts, there was a book where he shows that the time varying control can introduce the probability and the situations where you didn't have and this threshold control where the pedal will fall down, but if you start vibrating the base, you get a texture with respect to the rotation, and then you can swing it without any absolute more.
Yes, indeed, it is the same part with we started on this kind of problem. Because we start with this with the pendulum, where the vertex is vibrating failure. So with the field problem that we deal also some of the we can see here that kind of.
So it relates.
Yes.
So you play against the gravity here?
Yes.
You play against the gravity. So this is in some sense vibrational control.
Exactly. So I don't know the Professor Len Friedrich and the group Actuator work with this kind of problem. Generating motion and system. So for that reason, Professor Len Friedrich has tried to make explanation analytical analysis of this case. let's start with the non-smooth HPD control with mechanical system with actuator that's on. So, what is the problem with chain power transmission in robotic systems? Expensive, advantages, inexpensive, simple design, say, high power HPD capacities. But disadvantage, friction, that's not advantage. It's not a problem, but there are relevant and a lot of people deal with this kind of backlash and it's on. Like there's Touch, so on, and so on, Johnson. So, where the problem resides, the state and feedback controllers require joint position and part velocity measurements. So, this is a robot, an example of the robot taken from the which page. So, this is the actuator, and here is the position setting. But it could be increase the cost to manufacture this kind of robot because it's encoders and the robots and the actuators. So, but now encoders mounted in the motor can be easily implemented in the robots. Like in this example, this is the actuator, this is the encoder. So here is the same implemented in the robot. But we have backlash because the gear frame or the chains. What is the main problem here? We need to feedback position from the motor. But theoretical analysis for backlash also needs measurements for the link positionings. So this is not much realistic because it's not sense to have sensor here again and sensor here again. So how do you solve the problem of position regulation or position or tracking? Using only measurements of this site without sensing exactly the position of the link. So I'm going to, in this case, because of time, I'm going to avoid to avoid the different aspect of the machine quantum synthesis. And let's skip. So this one say the same term. So the simple machine quantum system prepares the solution of these algebraic mechanical equations. It depends on the linear dynamics of the system. The main elements it exists as a positive solution of the algebraic equations, and this along with this filter and this control, we have a local solution of the HPD control problem. So this is the main term that we're going to use. So now let's go to the problem. We have the actuator, the motor, the gear system, the load. So we have only position measurements from the motor, not from the load. But we need to guarantee that the load goes to the side position. So we take this dynamics from the motor and the load. Q1 is Q0 is the angular position of the load. Q1 is the angular position in the motor. Sorry for that. That was important. This is a model of the backlash for this one, given by this Nonsmooth equation. So the main problem of the control engine is to try the output to the set position today. It's simple to say that Q0 is not cannot as measured. Only Q1. So the dynamics of the aerodynamics of the motor and the load is simplified in this state space equation, and the aerodynamics of the motor becomes thoroughly stable. So in order to solve the HPD motor, we will depend on plant. We will find that say the output we control like this one, rho is a positive constant. The motor position Why is that only measurement available is in this case is P1, well, given by this unit expression, WY is the disturbances controlled to run the output, and how M is given by this simple expression. AR is positive, XS is depends is P1 is the position rule. So summarizing, looking all together, all the equations together, Fx P1, P2, is 1, H2, and are here. We need to linearize in order to solve the H infinity control problem. We use this theorem written in our paper from mathematics, where this feature gives the same like an observer of all the states, and this is a contour which depends on the estimated states. P is a positive determinant solution. So in experimental results, in a plan that we will you have this kind of plan. You have the model, the position sensor in the actuator. We put here a load position sensor in order to verify the results, not to feedback, just to verify the results. This is a backlash that we experimental obtain. And here our experimental result. Let's say this is the load position that tends to the desired position, while the motor position goes to any place. Don't care. The most important thing is that the load position motor goes to the desired position. Here is the same result with the under disturbance in case. The load position motor goes to the sub position, and the motor position goes to any place different the desired position. So final comments. We have process state stabilization out in certain load position. We follow the non-smooth test model of avalanche using the synthesis of the H in the corner. So our significant results on this topic was from our first paper from Professor Love, Jan Chakavio, and Professor Working in the Aspen Journal of the Dynamic System. Also with the group of Citedi and of students at NYU, we make some results with a fuzzy logic concept. So the new challenge is how to solve the same problem solution for the H infinity control to deal with this problem. Also, we have a result using tracking control problem to change velocity, and to deal with the same problem under unknown fields only. So the group of collaboration up to now is Professor Love, Professor Chakavio from Math, Professor Working from DIF, Professor Castillo from the Cáceres, of student, PhD student, which is Ponce, Master Sekipo, which is now PhD student, but it's not with me now, but make some contribution in these topics. I expect that Professor also we hear this list. So thank you. If you have questions?
This problem, I wonder if you need to know the characterization of the friction and the backslash.
Yes, it is.
So you need the information of the.
Yes. That's not. I need all this information. Yes. But we're still dealing with the point this kind of problem. We have simulations using assuming unknown level with respect to the model, but we not make the analysis to demonstrate that this is tell some level is not.